It's a pleasure to welcome you all once again to this course on Inferential Discrete Mathematics. In today's lecture, we will move ahead from where we stopped in the last class and learn a few more properties about lattices. Now, to give you a quick recap, we saw in the last class that a lattice is a poset for which any two pair of elements always has a specific element called as the least upper bound and another specific element called as the greatest lower bound. Whenever this property is being observed, your poset becomes what is called as a lattice. We'll discuss a few problems to get you into the groove of things so that you are familiar with the concept, and later we'll discuss a few more important properties and understand how this lattice gets the additional status as a Boolean algebra. We'll start with that. A simple example of a poset whose Hasse diagram is before you. Now you can recall that a Hasse diagram is the most efficient way to express a partial ordered set in form of a diagram. We have already seen this. Now we have a Hasse diagram of a poset, and we'll find out that this is also a lattice. It's clearly a poset because you have a Hasse diagram, which means it has to be a poset, and given any two elements of this set, the set containing the elements A, B, C and D, you'll always be able to identify one element called the GLB and the other element called the LUB out of this. You can pick any two elements of your choice. Let's say we pick A and C. Now you see that you have pairs AA, CC and AC. Since you have both AA and AC, A is clearly a lower bound. A is clearly a lower bound. And you don't have any other lower bound for both A and C in common. B is not a lower bound for A, so you can't have B as a lower bound, and D is obviously not a lower bound for C. So you have only one lower bound, therefore it automatically qualifies to be the GLB, the greatest of all lower bounds. Similarly, you have AC as well as CC, which means C forms of what you call as an upper bound. C forms an upper bound, and since there are actually more upper bounds here, you also have AD as well as CD, which means that D is an upper bound. You can't find any other upper bounds common to both A and C. Now both C and D are upper bounds. Now among these two, we'll have to identify whether we have the pair CD or you have the pair DC. You don't have the pair DC because strategically D is placed above the point C in the Hasse diagram. So this can't be part of the relation. You have only C and D. Now since you have CD, C is the least of the two upper bounds. The least upper bound is what you identify as the element C. Now that's what you see here. You pick two random elements, you'll always be able to identify both the GLB and the LUB of this pair. Now I've picked A and C. Now you can extend this exercise, consider BD or CD or AD. You'll always find a GLB as well as an LUB clearly defined, and hence this given poset represented by the Hasse diagram that we have here is actually a lattice. The next poset that we have is once again of the four elements A, B, C and D, but this poset is slightly differently structured. Now let's consider two elements here and find out what their upper bounds and lower bounds are. Let's pick the elements A and D. Going by the Hasse diagram, you will see that you have pairs AA as well as DD. You also have AD. You have DC also. So clearly A is in fact a lower bound, a common lower bound for A and D, and there are no other lower bounds available. Therefore A is the GLB. Similarly, you have DC and you also have AC. Now the pair AC, even though it is not represented by a direct edge in the Hasse diagram, you know that the transitive nature of partial ordering leads us to identify this pair AC. So you have AC as well as DC. So a common upper bound for both A and D can be C. Likewise, you have AD as well as DD. And since you have D and D as a pair, you also have A and D also as a pair, you will obviously see that D is also a common upper bound for both A and D. Therefore, you will see that both C and D are upper bounds for both A and D. Both C and D are upper bounds. Now among these two, one must be the least upper bound, and that has to be the element D, because you find only the pair DC but not CD. You don't find CD, you only find DC. Therefore, the two upper bounds are related in such a way that DC is a pair, and hence you will have D as the least upper bound and A as the greatest lower bound. Now this can be extended to other elements as well. You compare A and B, you will find GLB as well as LUB. Now just to go off on a relatively different tangent, consider what happens when I pick B and D. B and D are not actually related. If you consider the Hasse diagram, they are the same height from A. You don't have a direct edge and you don't have any transitive nature property connecting B and D. So B and D are not actually connected through an ordered pair. You find neither DB nor BD as a part of the relation. Both of them are absent in the given relation represented by this Hasse diagram. However, we are interested in finding out whether these two elements actually have a GLB as well as an LUB. Now considering that, you will see that the element A is a common lower bound for both A and D, because you have both AB as an ordered pair as well as AD as an ordered pair. Therefore A is actually a lower bound for the elements B and D, and that is the only element that's a lower bound. Hence you will see that there is no other lower bound for us to compare it with, and therefore A forms the GLB. Talking about upper bounds, you will find that you will have only BC as well as DC. Only the element C is a common upper bound for both B and D. Is a common upper bound for both B and D, and that's the only element. No other element is strategically placed above both B and D. There is no other element actually available, but no other element is strategically positioned above both B and D, and hence C is the only upper bound available. Therefore C is your least upper bound. As the only available upper bound, by default that becomes the LUB. Now look at a different poset expressed using this Hasse diagram. You have elements like this. Now my question is whether these two, this given poset actually qualifies to be a lattice. If you have a look at that, you will find that almost you can think about an ordered pair between any two elements. That won't be a problem except for two pairs. Now B and C are not related. You find neither BC nor CB part of the relation. So B and C are not exactly related to one another. Therefore B and C, you don't have an ordered pair available. But as we saw in the previous example, you will find an LUB in D and a GLB in A. That won't be a problem. So D is the least of all upper bounds available, and A is the greatest of all lower bounds available. So that's easily available. So every other element is actually connected by a direct edge or a transitive nature path. However, when you consider these two, that's what I'm getting to. When you consider these two, the element when you consider these two, the elements F and G, you will see that F and G have common lower bounds in D, C, E, B and A, but there is no upper bound available. You only find pairs FF and GG to support your evidence. They don't have any common. You don't have an element of the form Fy comma Gy. You don't have this pair. F is not related to any element on the top. There is no element above. That's kind of a ruled out thing, and therefore you don't have that upper bound available. There's no upper bound available, so nothing else to compare it with, and hence you don't have an LUB. And because of that reason, this poset that we have on our screens is not a lattice, because you find two elements for which only the GLB may be defined but the LUB cannot be defined, so that rejects the given poset from becoming a lattice. What about this? This, once again, this is a Hasse diagram showing the strategic positioning of 5 elements A, B, C, D and E. And here, if you can compare any two elements, you will find that you will always find both GLB and LUB present within the set. Take any two elements. Let's say we take B and D. B and D, there is no direct edge. Let's take elements B and D, but you have BE as well as DE. There is one common upper bound that obviously becomes the least upper bound. Likewise, you also find AB as well as AD, which means A forms a perfect lower bound for both B and D as a common lower bound, and that by default becomes the greatest lower bound. You can extend this and find the GLB and LUB for any pair of elements from the poset, and therefore this is actually a lattice. Moving further, what happens if you consider a different lattice, a one like this? We have trouble here. That is why I have highlighted this using different colors. As a matter of fact, you will see that this poset will not form a lattice. Why? Because there are examples for a pair of elements which do not have both GLB as well as LUB. An example of that is when you compare the elements B and C. Now, B and C do in fact have a common lower bound in A, because you have AB as well as AC. So A is the lower bound, and that's the only lower bound available, which means it by default becomes the greatest lower bound. However, if you try and list down upper bounds, there is trouble here. When you list upper bounds, you will see that the upper bounds of B are BB, you have BD, you have BE, and you have BF. These are all upper bounds. When we talk about upper bounds for C, you will have CE again, direct edge, CD a direct edge, CF a transitive path, and CC the reflexive ordered pair. So there are in fact common upper bounds available. Of course, this won't matter. So the common upper bounds available are E, D and F. Now it is obvious to see that there are common upper bounds, but none of them will actually be the least upper bound. Now if you can recall the least upper bound is actually an upper bound, so that any other upper bound is higher than it. So D is an upper bound because you have BD as well as CD. But D cannot be the least upper bound because any other upper bound, look at another upper bound, let's say look at the upper bound E. E is also an upper bound because you have both BE as well as CE. But what is the connection between E and F or E and D? Do you have DE or do you have ED? Unfortunately, you have neither. Both these pairs are not part of the relation. So what does the definition of the least upper bound say? Any other upper bound should be related with the least upper bound, any other upper bound. For that matter, F is actually an upper bound which is related to D. You have DF. You also have EF. That's okay. That part is all right. But look at D and E. They are not related. They are not considered for an ordered pair in this given relation, and that means this: neither D nor E can be the least upper bound for both B and C. Okay, what if we consider F? F clearly is an upper bound for both B and C. However, you see that FD is absent, you don't have FD. FE is also absent, you don't have FE, because F is strategically placed above both these points at a greater height compared from the point A. So you don't have both these. So F, though an upper bound, can only be an upper bound, cannot form the least upper bound, and that's why you don't find the LUB for the elements B and C, and just because of that reason this poset cannot be a lattice. It's only a poset, because there are a couple of elements which do not have an LUB. That's ruled out. This can also be argued in a different way. Let's compare D and E. D and E obviously have an LUB and F, because you have both DF as well as EF. That's the only upper bound, and by default that becomes the least upper bound. However, when you start finding the lower bounds, you will actually see that both D and E have three lower bounds. You have BD, you have AD, and you have CD. Similarly, you have BE, you have AE, you have CE. These are all lower bounds. So one of them may in fact get the extra status as the greatest lower bound. However, the same problem that we found with the LUB of E and D is also identified with the GLB of B and C. Now look at the GLB of B and C. A cannot be the GLB, because you have the relation that AB and AC are ordered pairs, but only that. But we saw that for the greatest lower bound you must in fact have BA as well as CA. Only then A becomes the greatest lower bound. You don't have that. This is not observed, so A cannot be the GLB. But can one of B and C be the GLB? Once again, you don't find a pair BC. You don't find the pair BC or CB. Both are absent. So therefore, all of B, A and C can be lower bounds, but only that. You'll have to stop. You have to draw the line there. You cannot have the greatest lower bound for this pair, and that's where we stop. So this is also a poset that is not a lattice. It's only a poset, nothing more. The same problem is identified once again here. This is once again a neatly positioned set of points which forms the Hasse diagram of a poset. However, this also cannot form a lattice, because when you pick elements C and D, they have a common upper bound in E, but they don't have a common upper bound which can become the greatest lower bound, because when you see the elements C and D, you have BC as well as BD, you have AC as well as AD. That's all right, no one's complaining. But among these two, you identify both A and B as lower bounds. A is a lower bound, B is also a lower bound, but among those two there's no relation. You find neither BA nor AB as a part of the relation. Both of them do not belong to the set of all ordered pairs represented by this Hasse diagram. So even though C and D have a common lower bound in both B and A, none of them are good enough to be called as the greatest lower bound. So they don't have a lower bound, they have an upper bound, they have the least upper bound, that's fine. But remember that a lattice is observed only when every pair of elements in a poset have both GLB and the LUB thing. That's not observed here, so this is also not a lattice. Okay, with that thing, we'll have a look at a couple of additional definitions. When do you call a lattice as a distributive lattice? A lattice L, which is comprised of an ordered pair of a non-empty set on which a partial ordering is defined, in such a way that it is reflexive, antisymmetric, transitive, and it also has the GLB and LUB for every pair, that lattice gets called as a distributive lattice if this property is observed. Only if this property is observed, it's called as a distributive lattice. Now you know these notations. When I say A join B, I am talking about the LUB of A and B, and when I say A meet B, I am talking about the GLB. Now if you find that this equation is preserved for any three elements A, B and C of the lattice, you will call the lattice as a distributive lattice. Further, a lattice LR, once again with all sufficient conditions to be met, all necessary conditions to be met, is called as a bounded lattice. It's called as a bounded lattice if it contains both the least element denoted by the symbol 0 bar and the greatest element denoted by the symbol 1 bar within itself. When you find both these observations, only then your lattice gets called as a bounded lattice. So we'll unanimously, uniformly refer to the least element as 0 bar and the greatest element as 1 bar. Now the next definition is about what is called as the complement of an element. Now let's consider two elements from a lattice L. The two elements be A and B. Now A and B are called complements of each other, or A is called as the complement of B and B is called as the complement of A if such a thing is observed. The LUB of A and B should be the greatest element of the lattice. The LUB of A and B should be the greatest element of the lattice, and the GLB of LUB should be the least element of the lattice. So the least upper bound should be the greatest element, the greatest lower bound should be the least element. If your lattice is defined in such a way such that there is a complement for any two elements, that lattice is what you call as a complementary lattice. And that's the definition we have here. Let LR be a bounded lattice. L is said to be a complemented lattice if every element of L has a complement in the same lattice. So every element, for every A you should be able to identify a B such that the join of A and B is the greatest element and the meet of A and B is the least element. Whenever you identify these two for any two elements A and B of the lattice, the bounded lattice L, then the bounded lattice gets called as a complemented lattice. Now since this definition is kind of new to you, we will discuss a couple of examples to make yourself familiar with this idea called a lattice. Now we have already seen that the pose set represented by this acid diagram is in fact a lattice. So I am not going to verify that nature of the pose set, we will just identify the complement. So let us say we pick the elements 2 and 3. What is the meet of 2 and 3 and what is the join of 2 and 3? The join of 2 and 3 is the least upper bound. Now the LUB of 2 and 3 is what you are trying to find. The LUB of 2 and 3 obviously happens to be 6. We have seen this before. Similarly, the GLB of 2 and 3 happens to be 1. The greatest of lower bounds of 2 and 3 happens to be just 1. From the diagram it is obvious that this property is observed. So 1 and 3, let us take 1 and 3. 1 and 3 has its least upper bound in 3 and 1 and 3 has its greatest lower bound in 1. So like this, for any two elements you can identify the complement as well as the GLB as well as the LUB. Therefore you can find out the complements of such elements here. 2 and 3 are complements of each other in this example. 2 and 3 are complements of each other. 1 and 6 are complements of each other. The GLB of 1 and 6 is 1. The LUB of 1 and 6 is 6 itself. because the least upper bound of 1 and 6 has to be 6. The greatest lower bound of 1 and 6 has to be 1. Therefore, you find that any two pair of elements has in fact the complement defined perfectly. And because you have this, 1 is not the complement of 3. 1 is not the complement of 3 because the join of 1 and 3, the least upper bound is 3, it's defined. Because it's a lattice, 3 will obviously be the least upper bound and it's part of the set. But that's not the greatest element. 6 is in fact the greatest element and 1 is the least element. And since the join of 1 and 3 is not the greatest element, 1 and 3 are not complements of each other. However, if you pick 1 and 6, 6 will happen to be the LUB and 1 will happen to be the GLB. 6 happens to be the greatest element, 1 happens to be the least element, therefore 1 and 6 are complements. The same was observed with the pair 2 and 3. 2 and 3 had its LUB in 6 and the GLB in 1. And therefore, 2 and 3 are complements of each other. 1 and 6 are complements of each other. There are only 4 elements and we have already found out the complement of every element. 1 is 6 is complement, 6 vice versa again, 1's complement, 2 is 3's complement and 3 is the complement of 2. Hence, what you have here is a complementary lattice. Let's take a different example now. The set of all divisors of 20. 20 has 6 divisors in itself, 1, 2, 4, 5, 10 and 20, and they are related by the relation A divides B. That's what you see here, 1, 5, 1, 10, 1, 20, 1, 2, 1, 4, because 1 divides every number, 5, 10, 5, 20, 5 only divides these two, 2, 4, 2, 10, 2, 20, 2 divides all of these, 4 divides only 20, 10 divides only 20, 20 is divided by every other number. That's how this relation is constructed. However, when we try and find the complement of these elements, there are 6 elements here. It is obvious that 1 and 20 are complements of each other because the LUB of 1 and 20 is 20, GLB of 1 and 20 is 1. 1 and 20 are complements of each other. 4 and 5 are complements of each other. The LUB of 4 and 5 is 20 because only 420 and 520 are obtained. No other number is obtained. 20 is the only upper bound and therefore it is a LUB. And the common lower bound happens to be 1. So the GLB is the least element, the LUB is the greatest element, you have the complement defined. However, when you pick 2 and 10, we run into trouble. When you pick 2 and 10, the greatest lower bound of 2 and 10 happens to be 2 because you have 2, 2 as well as 2, 10. You have 1, 2 as well as 1, 10, but between 1 and 2 you have only 1, 2. So 2 is the greatest of all lower bounds. So that's not the least element. 2 is not the least element. The lattice has its least element in 1 because 1 divides every other element, 2, 4, 5, 10, 20. Therefore, 2 is not the least element, and similarly the join of 2 and 10, which is the least upper bound of 2 and 10, is in fact actually 10 because you have 2, 10 as well as 2, 20, you have 10, 10 as well as 10, 20. So 10 is in fact an upper bound and the least of all upper bounds. Between 10 and 20 you have only 10, 20, you don't have 20, 10. So both 10 and 20 are upper bounds of both 2 and 10, but they are related only in this manner. So 10 is actually the LUB, but 10 is not the greatest element. The greatest element here is in fact 20 and not 10. Therefore, even though you have least upper bounds and the greatest lower bound for both 2 and 10, you will obviously have, because the poset is actually a lattice, but it's only a lattice, it's not any further. You can't call it as a complementary lattice because you have elements 2 and 10 which are not complements of each other. The complement of 2 is not defined in this set. You will never find an x such that 2 join x is 20 and 2 meet x is actually 1. You will never find an x. So 2 and 10, you don't find a complement for 2, you can't find a complement for 10, and therefore the complement is not defined for every element of the set, and that's why this is not a complementary lattice. Not a complementary lattice. Because 2 and 10, that's the problem with 2 and 10. 2 and 10 are not complements of each other. The complements of 10 and 2 cannot be individually found, and therefore this is only a lattice and not anything more. Let's take D30 for example. Now D30 takes care of all divisors of 30. 30 has its divisors 1, 2, 3, 5, 6, 10 and 30. Now if you'll be able to find out that it is a lattice. Okay, I'll leave that part to you. You'll obviously be able to see that it is a lattice. Now what we are concerned is in the complement of every element. Now in the previous example we saw that D20 was not a complementary lattice because certain elements did not have complement elements defined within the set. Therefore it's not a complementary lattice. But what about this? Can you find complement of every element? Now there are 8 elements in all. Let's try and exhaust all possible pairs. Let's say we take 3 and 10. You don't find an ordered pair 3, 10 because 3 doesn't divide 10, 10 doesn't divide 3. So let's consider these individual elements called 3 and 10. Let's take the elements 3 and 10. What can be the LUB of 3 and 10? A possible upper bound for both 3 and 10 together, and a possible GLB for both 10 and 3 together. Now 3 and 10 together divide 30 and only 30. They don't divide 6 together, they don't divide 15 together, they don't divide 5, 2 or 1 together. So you will find the pairs 330 as well as 1030. So 30 is in fact an upper bound and the only upper bound. So 30 obviously is the LUB and 30 is the greatest element of the given lattice. Every other number divides 30. 30 is the greatest element of the lattice. Similarly, the lower bounds, you don't find any other lower bounds for both 3 and 10 together. 5 divides 10 but 5 doesn't divide 3. 2 divides 10, 2 doesn't divide 3. Only number that divides both 10 and 3 is 1, and 1 happens to be the least element of the lattice. So now you see the LUB is the greatest element, the GLB is the least element, which means 3 and 10 are complements of each other. Likewise, you will also be able to see that 2 and 15 are complements of each other because the LUB of 2 and 15, the only number both 2 and 15 divide together is 30. And the only number that divides both 2 and 15 is only 1. So the LUB is the greatest element and GLB is the least element. So once again you will find a complement of 2 in 15 and a complement of 15 in 2. You can also extend this to the pairs 5 and 6. 5 and 6 are such that the LUB of 5 and 6 is 30 and the GLB of 5 and 6 is 1. Once again 1 being the least element and 30 being the greatest element help us identify that 5 and 6 are complements of each other. So we've already exhausted the pair 3, 10 which are complements of each other, the pair 5, 6 each other again, 2 and 15 again. The only ones that are left out are 1 and 30. 1 and 30 is obvious. The only bound for 1 and 30 has to be 30 and the GLB has to be 1 again. So 1 and 30 are complements of each other, 2 and 15 are complements of each other, 5 and 6 are complements of each other, 3 and 10 are complements of each other, and hence the lattice actually gets the additional status as a complementary lattice. Not only a lattice, also a complementary lattice. Okay, let's pick one more example. Well, this time the trouble is with that this is actually a lattice. There's no trouble with being a lattice. However, when you pick C and E, the elements C and E, they have their least upper bound in D, because both CD as well as ED are found. So it's actually a bound for both C and E. The least upper bound of C and E is in fact D, but that's not the greatest element. The greatest element we have seen before is the one element that's strategically placed on the top of the Hasse diagram, topmost element. Topmost element happens to be F, because every number is related to F. CF, EF, BF, AF, DF, all of these are related to F. So C and E actually have a least upper bound. So because it's a lattice, they have a least upper bound, but that least upper bound is not the greatest element. So C and D are not complements of each other. You can't find the complement of C from this set. And because of that reason, this one cannot be a complementary lattice. This is not a complementary lattice. Lattice nonetheless, because you will be able to find out both GLB and LUB of every element given here, but they don't turn out to be the greatest or least elements, and that's why there's only a lattice. Next again is a very differently set of points here, forming a nice Hasse diagram. But the problem here is the positioning of elements. Now when you look at these, you will see that E and F, the elements E and F, have their upper bound in G, which happens to be the greatest element. They have an LUB, all right, no one's complaining that part, but the GLB part, the GLB of E and F, the common lower bounds are D, B, A and C, but the GLB actually happens to be D. The greatest of all, the one lower bound that's strategically placed at a higher position among all lower bounds A, B, C, D is D again. So the greatest lower bound is D, but that's not, unfortunately, the least element. The least element of this set, this lattice, turns out to be A, because A is the positioned at the bottommost part of the Hasse diagram. So A is the least element, that's not the GLB of E and F, and therefore E and F are not complements of each other, because their GLB is not the least element. You can proceed further and also say that B and C don't have their LUB in G. Look at the join of B and C. The join of B and C happens to be D. Once again, D is also not the greatest element. D is not the greatest element. The greatest element that we have already identified is the element G. And since D, which happens to be the join, the least upper bound of B and C, is not the greatest element, B and C are not complements of each other. You can explore further, and you will see that they don't have complements here, and therefore this is not a complementary lattice. Well, that brings us to this next idea on the Boolean algebra. Boolean algebra is what can be expressed as the foundations for something called as circuit building. A little later we'll find out what connection it has with this subject called the designing of circuits in the most efficient manner. Now for that you need a lattice, and that's what you have as a definition. A Boolean algebra is a lattice B that contains, first of all, the least element as well as the greatest element, and is both complemented. Now when you call complemented, for every element I am able to define a complement. That's like a few examples we saw a little while back. It also needs to be distributive. Now whenever a lattice meets all the conditions, condition number 1, it should have both the greatest and the least element. Condition number 2, it should be a complemented lattice. Condition number 3, it has to be a distributive lattice. Now if that's the case, then your lattice gets the additional status as a Boolean algebra. It's called as the Boolean algebra. Now we've already learned what an algebraic structure is. An algebraic structure is a set with a few operations. It can be a group where the operation needs to be binary. Here we have an algebraic structure which talks about a set and 3 operations: number 1 disjunction, number 1 conjunction, number 1 complementation. This is where we draw the bridge between this unit on lattices and the first unit that you studied on logic. Logic, we saw that there can only be 3 forms of connectives. Either you negate something which is akin to the complementation, you combine them in form of a disjunction or the conjunction. That's what we saw in the first unit. Now here we will try and bridge the units 1 and 5. What was logic and what is the unit on lattices? We will bridge both. Before that, we'll have a look at a couple of examples. Now you will see that this is a lattice. You've already seen this. And we also see that 1 and 6 are complements of each other, 2 and 3 are complements of each other. That it is also easy to verify that it is distributive, and hence this forms a Boolean algebra. This again is a Boolean algebra. There are only 2 elements A and B. They are their GLBs and LUBs again, which means they have complements defined for all elements of the set. It is distributed obviously, therefore it is a Boolean algebra. This won't be a Boolean algebra because we already see that E does not have a complement, because there is no such element X such that E subscript, the join of E, in fact the meet of E and Y is A. You can't find any other element, because we have already seen the GLB of E and F is actually D, and D is not the least element. Therefore this is not a complemented lattice. It's only a lattice nonetheless, but only an ordinary lattice. It's not a complemented lattice. We have another poset here, but this poset is not even a lattice because these two don't have an upper bound. The elements C and E don't have an upper bound. The elements A and F don't have a lower bound. So they don't even form a lattice because there are a couple of elements for which the upper bounds don't exist. If the upper bounds don't exist, LUB is not defined. If the lower bounds don't exist, GLB is not defined. And since this is not even a lattice, forget distributive, forget complementary, it is not even a lattice, and we draw the line there. Okay. Moving ahead, we saw this as a lattice. It's the most popular, frequently used given example for a lattice. However, we'll see that it is not complemented, because when you pick elements B and D, the join of B and D is D, and the meet of B and D is C, and it is not actually the greatest element. The greatest element of this lattice happens to be E, because every number is related to E, and the least element doesn't happen to be A, because A is related to every number and C is not A. So despite being a lattice, a beautiful lattice in itself, this is not complemented, and since it is not complemented, it cannot form what we call as a Boolean algebra, because we saw that a lattice should have the greatest element and the least element. A lattice should be distributive, a lattice should be complemented. This is not complemented, and hence it cannot form a Boolean algebra. Here, this we already saw. We saw that this is A, first of all, a lattice, B, it is bounded, it has a least element in 1, it has a greatest element in 30, it is bounded clearly, you can verify that it is distributive. However, you also find that it is complemented. 2 and 15 are complements of each other, 5 and 6 are complements of each other, 3 and 10 are complements of each other, 1 and 30 are complements of each other. For every element there is a complement defined. Therefore, it is complemented. It is the lattice, it has both the least and the greatest element, it is distributive, it is complemented, and hence it forms a Boolean algebra, unlike the previous example which was only a lattice. Now, next up we'll have a pair of easy results to find out whether the given lattice actually forms a Boolean algebra. We'll use a couple of necessary conditions to help us identify this. A finite lattice, look at the first requirement, your lattice should be finite. A finite lattice which cannot be isomorphic to Bn, the set of all binary strings of length n, cannot be a Boolean algebra. A binary string is easy. A binary string is a string of characters where every number is either a 0 or a 1. So when I try and write a binary string of length 6, this can be 0 or a 1, this can be 0 or a 1, this can be 0 or a 1 everywhere. So every position of the string has two choices, and therefore you'll have 2 power 6 strings available. Now what does it say? The conditions say any finite lattice which is not isomorphic to Bn, or any finite lattice L whose number of elements is not 2 power n, because you'll obviously have 2 power n elements in Bn, cannot be a Boolean algebra. That is the reason why we saw a while back, this was a lattice, this is a finite lattice, but how many elements you have? There you have only 5 elements, and 5 definitely is no integer power away. 2 raised to 1 is 2 power 1 is 1, 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8, 5 comes nowhere. So the number of elements is not a power of 2, and if that's not followed, you cannot have a Boolean algebra. So what does it say? If a lattice is not isomorphic to Bn, it cannot form a Boolean algebra. Or a Boolean algebra is a finite lattice with these many elements. Second, and the most interesting of the conditions that we learn is a poset Dn can become a Boolean algebra if n is factorized as a product of prime numbers, not even powers of prime numbers, only prime numbers. If that's the case, if that's how you factorize n, then the corresponding Dn will obviously be a Boolean algebra. That's what this result says. Now we'll check it out. This is definitely a Boolean algebra because it has 2 power 2 elements. There's only 4 elements. So the lattice, we already saw that it is a lattice, and it is finite, it has only 4 elements. It has the number of elements is a power of 2. So this is in fact a Boolean algebra. We have already verified this using the concept of the complement and the bounds, etc. But this will also help us arrive at the same conclusion. And this, we saw that this is not a Boolean algebra. And how do you identify that? The number of elements is 6. The number of elements here is 6, 1, 2, 3, 4, 5, 6, which is not a power of 2, so it cannot form a Boolean algebra. And lastly, when you factorize 20, it's 2 raised to 2 times 5 raised to 1. You don't have 2 times 5. You have a different power of 2, a power of 2 that's different from 1. So it doesn't have 2 power n elements. It is factorized not as single powers of prime numbers, and hence it is also not a Boolean algebra. So one other way of quickly determining what lattices will form Boolean algebra, we can use these 2 necessary conditions. This We saw this to be a Boolean algebra. I'll show you how it fits the bill here. 30 is actually factorized as 2 times 3 times 5. Each term here is a single power of a prime number. 30 is 2 times 3 times 5. So D30 will be a Boolean algebra. And look at how many elements you have. You have 1, 2, 3, 4, 1, 2, 3, 4. You exactly have 8 elements. So it is isomorphic to B3. B3 will have 2 power 3 elements. You find that. So this will definitely form a candidate which can become a Boolean algebra, unlike the previous 2 examples. This is even worse. The number of elements here is only 7. 7 is not the same as any power, any integer power of 2. Number 1. And number 2, that's it. A finite lattice should be isomorphic to Bn. 7 is never an integer power of a 2. So this is also not a Boolean algebra. We've already seen why that condition is observed. E and F will have a GLB which is not the least element. B and C will have an LUB that's not the greatest element. Therefore it is not complemented, and therefore it is not a Boolean algebra. This is again easy. We have solved this before. It has 5 elements, and 5 is never same as any integer power of 2. Not the same as any integer power of 2, and that's why this will also be only a lattice, nothing more. What if you consider D385? Now D385 talks about all divisors of 385. How do you factorize 385? 385 is 5 times 73, I guess. 5 70s are 350, and another 15 is 385. No. 5 times 38, is it? Yeah. 37 in fact. No. 5 times 77 is what we have here. 3 times 85 is 5, 3 times 385 is 5 times 77. So it's clearly, you write it as a product of 5 times 7 times 11. And we saw that whenever you factorize Dn and the n as a product of single powers of prime, it will happen to be a Boolean algebra. That's what we see. So this is in fact, this will be a Boolean algebra. You can check it. You will have only 4 elements here. You'll have how many elements here? I think you'll have 8 elements. What are they? You'll have 1 divides 385, 5 divides 385, 7 divides 385, 11 divides 385, 77 divides 385, 77 and 5 give you 385, 35 divides 385, and 55 also divides 385, and you also have 385. So the lattice of this will look something like this. 385 at the topmost, 1 at the bottommost. You have 5, you have 7, you have 11, you have 35, you have 77, and you have 55 also. All of them divide 385. That's how we have the lattice diagram or the Hasse diagram defined for this lattice, and you will in fact be able to find out the complements of all numbers given here. In fact, 5 and 77 are complements of each other. 5 and 77 have their least upper bound in 385, the greatest lower bound in 1. 7 and 35 are complements of each other. Their greatest lower bound is 1 and least upper bound is 385. 11 and 55 are complements of each other. Their LUB is 385, their GLB is 1. We have covered 3 pairs now. The only pair left is 1 and 385. 1 and 385 are complements of each other. Their LUB is 385 itself, and their GLB is 1 itself. So every element has a complement, and it's distributive, and is a lattice, therefore it will form a Boolean algebra. But you can also verify that using the two results I already told you. It has 8 elements, which is isomorphic to 2 power 3, and you can factorize it as a product of single powers of prime numbers. What about 60? The problem with 60 is the number of elements. D60 will have 1, 2, 3, 4, 5, 6, 7, 8, 9 are ruled out, 10, 12, 15, 20, 30 and 1. It has in fact 12 elements, and 12 is no power of 3, no power of 2. 12 is no power of 2. And when you factorize 60, you will have to do as 2 square times 3 times 15. The powers are not single powers of prime numbers, you have 2 power 2. That also helps us identify that this lattice, even though it's a lattice, can only be a lattice, cannot become a